Section 3.4, Graphing Polynomial Functions. So we are back to graphing in this section. We did some graphing in 3.1 and 3.2. We graphed linear and quadratic functions, and both of those are actually types of polynomial functions. But here we are going to be looking at polynomials that are higher than degree 2, so degree 3 or degree 4 polynomials. And we are going to start with some definitions. Let's recall what whole numbers are, and you probably already know this, but just in case, make sure that you know 0 is included. So the whole numbers are 0, 1, 2, 3, 4, 5, and so on. And another definition we want to review is the degree of a polynomial. It is the highest, the degree is the highest exponent on the variable. So with that in mind, here it says to be a polynomial function. So this is kind of like a definition for polynomial function. All the exponents on the variables must be whole numbers. Remember, that includes 0. The exponents could be 0, 1, 2, 3, so on. And because of that, we can say the exponents cannot be negative numbers. Negative numbers are not whole numbers. They cannot be fractions, and they cannot be decimals. Okay? So when you are looking to see if you have a polynomial function, look at the exponents. They have to be whole. They cannot be negative. They cannot be fractions. They cannot be decimals. And another thing that's important is the variable cannot be in the denominator. The variable in the denominator is actually the same thing as a negative exponent. I don't know if you guys recall the exponent rule that says x to the negative, we'll just say n, equals 1 over x to the positive n. So if I had something in the bottom like 1 over x squared, that is the same thing as x to the negative 2. So if you have a variable in the denominator, it is not a polynomial function because it is the same thing as having a negative exponent, which is not a whole number. So let's practice that concept with these problems. It says determine which functions are polynomial functions. So you can just answer yes or no. For those that are, identify the degree. So number 1, focus on the exponents on the variable. So we start out here in our first term. We have x to the 6th. Our exponent is a 6, which is a whole number. The second term, the exponent is a 3, which is a whole number. And on our third term, we have x. We do not see the exponent, but if you see just an x, there's an invisible 1 as the exponent. So all the exponents are whole numbers. Then we would say, yes, this is a polynomial function. And if the answer is yes, we are going to also tell the degree. The highest exponent, so the degree is 6. And that is our answer for number 1. Now, notice, just for a sec, the coefficients. We have a 5 pi and a negative 3/4. So those are not all whole numbers. 5 is, but pi is not, and negative 3/4 is not. And that's okay. The coefficients do not have to be whole numbers, only the exponents. Okay, look at number 2. Right away on our first term, we have an exponent of 1/3. 1/3 is not a whole number, so we can go ahead and just answer no. And that's all you have to write as far as on a quiz or a test. But if you're trying to make yourself some notes as to why you answered no, then you would write because 1/3 is not a whole number. Okay, let's try a couple more. Number 3 looks a little different. You could rewrite it if you would like. I'm going to go ahead and show you that. Remember, when you have one term on bottom, it could be written underneath each term on top. So we could put it underneath each. Then I'm going to show you one other thing. When you have the variable, you could also say, well, okay, I know there's a 1 in front. Let me write that as 1/5 x cubed, with the x cubed to the side instead of the numerator. They mean the same thing, but this way we can see our coefficient is 1/5, variable, and exponent. And then on the second term, 1/5 x squared. And then our constant would be that minus 2/5. And this looks more like the form that we are used to for polynomials. So now let's look at our exponents. First term, exponent is 3. That's a whole number. Second term, exponent is 2. That's a whole number. Third, we don't have a variable here. However, it could be written as x to the 0 power. And remember, 0 is a whole number. The reason you can do that is because this is another exponent rule. X to the 0 is 1. No matter what x is, anything to the 0 power is always 1. So if I wrote negative 2/5 times x to the 0, and then I replace x to the 0 with 1, then it still is just negative 2/5, okay? Which is how we normally write it. We don't normally write x to the 0 behind it. I just did here so that you could see the variable with the exponent. And now you know all the exponents are whole numbers, and so your answer to the question is yes, this is a polynomial function, and the degree is our highest exponent, which is 3. So that is the answer. Okay, one more example of this, number 4. Right away, hopefully you notice there's a variable in the denominator. And when you see that, you can just answer no. This is not a polynomial function. And if you want to put a reason there, you can say there's a variable in the denominator. Remember, that's the same thing as having a negative exponent. So if I have a, let me rewrite it, 8x cubed minus 2 over x is the same thing as a minus 2x to the negative 1. So you don't have to know that necessarily for this section. Later on, we will work more with that. If you just want to say it's because the variable's in the denominator, that's good. But I just want to go ahead and show you this as well so you can see your exponent is not a whole number there. And when the answer is no, you do not need to give the degree. It doesn't really have a degree if it's not a polynomial. Okay, so now we hopefully have an understanding of what polynomial functions are, what their equations are going to look like. But what are their graphs going to look like? Well, we have 2 words to describe the graphs. They are going to be smooth and continuous. Smooth means anytime it curves, it's a rounded curve. It has no sharp corners. If it goes from increasing to decreasing or vice versa, it will have a rounded curve. And continuous means it will have no breaks. It can be drawn without lifting your pencil. The whole graph, you can draw it without lifting your pencil. So remember I said earlier, we've already graphed linear functions. Those are lines. Let's just draw one here. That is smooth because it doesn't have any sharp corners, and it is continuous. I can draw the whole thing without ever lifting my pencil. We've also done quadratic functions, and they are parabolas. They may open up, they may open down, but notice they are smooth. They are rounded curves, and they are continuous. One smooth curve, there's no breaks in it. We can draw it without lifting the pencil. Now, the nice thing about the linear and the quadratic are we know those shapes. But when we get into third or fourth degree polynomial functions, we are not going to know the exact shape. But we do know these two things. We know the graphs are smooth and continuous. So it might look something like this. It might look something like this. It'll always be smooth and there will not be any breaks in it. Like that. Which we should recognize that shape as the shape of the cube function, which is also a polynomial function. Okay, so on the next slide, we are going to look at some graphs. And the question is, determine which graphs are polynomial functions. So again, here you can just answer yes or no. So graph 1, it's rounded every time it changes directions. It's rounded. It has no breaks in it. It's smooth and continuous. So yes, this is a polynomial function. And if you were giving a reason, you would say because it is smooth and continuous. Look at number 2. This one, we see that when it changes from decreasing to increasing, it has a very sharp corner there. That means it is not a polynomial function. So you can answer no. And my reason would be because it has a sharp corner. And you hopefully recognize that this graph is the graph of an absolute value function because it has the V shape. Okay, so because we do not know the shapes of these functions, we know they're smooth and continuous, but we don't know their exact shapes, then we're going to figure out some things about the graph that will help us to be able to draw these. And one of the things that we can determine is the end behavior. End behavior means what is the graph going to do on the left end and on the right end. And we can determine this from looking at n, which is the highest exponent or the degree, and a, the leading coefficient. Those two numbers will tell us what the ends are going to do. So let's start with looking at n, the degree. If n is odd, the ends go in opposite directions. Think about a line. The degree of a line, a linear function, is 1, degree 1. Okay? And we know that when you draw a line, like we have here on this table, the ends are going in opposite directions. The same thing would happen for the cube function, right? Degree 3 is odd, and those ends go in opposite directions. Think odd, opposite, O and O. When n is even, the ends go in the same direction. Think about a quadratic, which is degree 2. We draw the parabola, either both ends are down or both ends are up. Okay? So when n is even, the ends go in the same direction. Now, once we've determined that, we need to go a little bit further. So if I know they go opposite, well, how am I going to know which end goes up and which end goes down? That's going to be determined by A. A is my leading coefficient. If A is negative, less than 0, the right end, always think about the right end, goes down. Okay? It falls because if it were degree 1, that would be your slope, and it causes the line to fall. So if you can think about what a negative slope does, that's going to help you learn that when A is negative, the right end falls. If A is positive, think about a positive slope. It rises. Okay? The right end behaves like the slope, okay? The slope of a line. Now, once you've drawn the right end, if they go in opposite directions, then you know just draw the other one opposite. And really the same thing here. You can say, okay, what is the right end going to do? When A is negative, it's going to fall. When A is positive, it's going to rise. Now, if n is even, though, the other end does the exact same thing. Or you could remember with the quadratics, which we just recently studied, when A was negative, it opened down, so the ends both go down. When A was positive, it opened up, so both ends up. So don't really think about, oh, I'm going to have to memorize this whole chart here. This is called the leading coefficient test, by the way. And don't really try to memorize it. Just use things we've already learned about linear and quadratics to apply to any odd or even degree function. Now here are some other things we are going to find when we start graphing. We will find the x-intercepts, the y-intercept, and we'll find the maximum number of turning points, and we're going to need a few extra points to make a good graph, and we will plot those and remember to sketch a smooth, continuous graph. Now we're going to come back and talk more about these different things that we're going to find when we start graphing. But first, let's practice that end behavior. So read the instructions. It says, determine the end behavior of the graph of the polynomial function. So make sure you know what it means when it says that. Okay, let's look at number 1. Our terms are in descending order. My highest exponent is a 3. That's the degree. So we're going to call that n. n equals 3. Now, what we need to know about that is whether it's odd or even. In this case, it is odd. So that tells me the ends are going to go in opposite directions. N is odd. The ends go in opposite directions. Then the next thing I'm going to look at is A. A is my leading coefficient. So A is -7, less than 0. So A is negative. Then that tells me, I think about my right end, okay? My right end falls like a negative slope. Right end falls. And then what I want you to do is just draw that for me. We are going to draw it and not use words. So my right end is going to go down. My pen keeps messing up, sorry. Right end goes down. Put an arrow. Falling from left to right, it's going down, it's falling. Now we know because of n being odd, they go opposite, therefore my left end is going to go up. So draw the right end and then just draw the left end kind of parallel to the right end, but with the arrow going up instead of down. And this is the answer. This is our end behavior. And we actually know what an x cubed, just a basic x cubed function looks like. The negative just makes the ends do opposite of what x cubed normally does. Okay, look at number 2. Now this one is in factored form, so you can't actually just look to see what the degree is. You could multiply it all out, although that is unnecessary. Let's just think for a moment what would happen here. We've got 5 and we've got x plus 1 and then 3 x minus 4s. Now let's just think about multiplying all of the x's together. So you've got x times x times x times x is going to end up being, you'd still have your 5 out front, and x to the 4th. Now, it doesn't matter what all the other terms are because that would end up being the degree. Okay, n is 4. Now, you could also get that by just adding the exponents of your factors. This x plus 1 is 1, and then you've got your 3 here. If you add the 1 plus 3, that would give you your degree. So it is not necessary to actually fully multiply all of those out. But n is 4, it's even, so that tells me the n's are going to go in the same directions. Both n's go in the same direction. Now I'm going to look at my leading coefficient, which is the 5. A is 5, positive. Okay, so when it's positive, it tells me right end rises. Think of a positive slope. It goes up from left to right. Now, because the ends go in the same direction, my left end also goes up, but it's not going to be parallel. When n is even, they're going to kind of go off the other direction, so up to the left. They both go up. Think about it how a parabola does, and then you can get an idea of what your ends are going to do. Notice we're not connecting them because we don't know from this what's going to happen between the ends. It might be something like, that was not a good graph. Let's say something like this. Or maybe it could even have more turns in it. Okay, but we know that the ends go up. We just don't know what's going to happen in between them yet. We'll work on that part later. Okay, so that's end behavior. Make sure you practice that in the homework and see exactly how the ends are drawn in the answers. Next part, we will be finding the x-intercepts. Now, there are a few things we need to go over first. Okay, we've already talked about zeros or roots, but we have that again here. So let's review that those are the values of x for which the function equals 0. Sorry, that should be raised a little bit. This f of x equals 0. So you set your function equal to 0, you solve, you get the zeros or the roots, and those zeros appear as x-intercepts. Now here's a new word for us, multiplicity. It's the number of times a zero occurs. So let's say I have a function that is degree 3. Okay. The degree tells me how many zeros or roots I'm going to have. So I'm going to have 3 zeros. But they do not all have to be different. Okay. It could be that I get x equals 1, x equals 1, and x equals 2. So that's 3 zeros of the function. However, this one occurs twice, so we would say x equals 1 has multiplicity 2. Okay? X equals 1 has multiplicity 2. Now the multiplicities will always add up to the degree. So if you have x equals 1 with a multiplicity of 2 and x equals 2 with a multiplicity of 1, we add those 2 plus 1 equals our degree 3. We normally do not write x equals 1 twice. We just say it has multiplicity 2. Now, why does that matter? Well, it is going to help us draw the graph. Look at the next part of the slide. If a zero has even multiplicity, the graph touches the x-axis and turns around. Even multiplicity, it's going to touch the x and turn around. If it has odd multiplicity, the graph will cross the x-axis. So let's draw a number line down here. Let's let this be our x-axis. And we're going to put some x-intercepts on here. So here's our first one. And let's say this x-intercept has multiplicity, I'm going to abbreviate that, 1. Well, 1 is odd, and so when we draw the graph, we know we should just cross. So we're down here and we cross right through our x-intercept. Now let's say this one has multiplicity 2. 2 is even. So that means it's going to touch. Let's just say we're starting up here. We hit our x-intercept. We're going to touch it and turn around. Make it smooth. Mine doesn't look very smooth, but touch it and turn around. Those are the main concepts. Now there's one other thing that will help also. It says when the multiplicity is odd and greater than 1, the graph flattens out. So let's say here's another x-intercept, and it has multiplicity 3. So it's still going to cross because it's odd, but it's going to kind of flatten as it crosses, kind of like x cubed does. And so here's multiplicity 1, just crosses right through, but if it's odd and greater than 1, it's going to flatten as it crosses. So that is why the multiplicity is important. It's going to help us to know how to draw the graph at the x-intercepts. So let's just practice that before we go on. Find the zeros for each polynomial function and give the multiplicity for each zero. State whether the graph crosses the x-axis or touches the x-axis and turns around at each zero. Okay, so here we are again with that function we looked at a moment ago that's already in factored form. Now again here, it is not necessary for me to multiply it all out. In fact, it helps me that it is factored. I am going to, when I'm finding the zeros, I'm going to set the function equal to 0. Just like when we have been finding the x-intercepts in 3, 1, and 3, 2. Set it equal to 0. We would factor it if it wasn't already, but it already is factored. So we're ready to set each factor equal to 0. Now -5 is just a number. If it doesn't have an x, I don't set it equal to 0. But I'm going to set the x plus 1 equal to 0 and the x minus 4 equal to 0. Each different factor. And I'm going to solve those, and I get x equals -1 and x equals 4. Those are my zeros of this function. If I were graphing, those would be my x-intercepts, -1 and +4. Now, it wants us to give the multiplicity. So we'll just abbreviate that. The number of times that answer occurs, and we can determine that by looking back at my factors. Okay, well there was only one x plus 1. You can't see it, but there's an invisible 1 as your exponent there. So this has multiplicity 1. And then on my x minus 4, there's actually 3 of those. You don't have to write it out 3 times. But if we did and we solved each one, we would get x equals 4 3 times. And really the easy way to get those multiplicities is just to look at the exponent on the factor. So x plus 1 had an exponent of 1, multiplicity 1. And the x minus 4 had an exponent of 3, making this multiplicity 3. So we might make a note here that these are the exponents on the factors. Now notice if you add them together, the multiplicities equals 4, and we had already determined that the degree of this is 4 in our previous example when we were doing the end behavior. And that again comes from adding the exponents, or from thinking of it as x times x times x times x is x to the 4th if we had multiplied all that out. So n is 4, the multiplicities must add to 4. Okay, then one more part. State whether the graph crosses or touches the x-axis. When the multiplicity is odd, it will cross. You can just write cross. Now multiplicity 3 is also odd. It's going to cross. And if you want to be a little more specific here, we already looked at the previous slide where it said if it's odd and greater than 1, it will cross and it'll flatten as it crosses. So I'm going to go ahead and add that. So all of this is our answer for number 1. Let's try another one. Okay, so this one is not in factored form. We're going to set it equal to 0. And we are going to try to factor it ourselves. So we do have a GCF of x. Let's pull that out. And then let's see if we can keep factoring. We've got our x. Now this trinomial can also factor. We need x here and x here. Factors of 4 that add to be 4 are 2 and 2. Same signs, both positive. And you could leave it like that, or you may want to write it x plus 2 squared. Okay, set each factor equal to 0. So we're going to take just this x right here, that needs to set equal to 0, and the x plus 2 equal to 0. This one needs to be solved, so we subtract 2 on both sides. So the zeros are 0 and -2. Now for the multiplicity. Let's start with the first one, x equals 0. And go back and look at your factor that it came from. It came from x. X has an exponent of 1. So this has multiplicity 1. And then we need to look at our other factor, x plus 2 is squared, which you can actually see above that. There are 2 of those. So x equals -2 occurs twice. Multiplicity 2. And notice when you add 1 plus 2, you get 3, which is the degree. Look back at your original function. This one we can actually see the highest exponent. It is degree 3, and that's what our multiplicities add to. Okay, one more part. Let's say touch or cross. So let's look at the first one. Odd multiplicity, 1 is odd. Doesn't matter whether the zero's odd or even, but the multiplicity. So multiplicity is odd. That means it's going to cross at x equals 0. In this second one, the multiplicity is 2. That's an even multiplicity. So when we draw the graph, it will touch the x-axis at -2 and then turn around. You can just write touch, that'll be fine. And let's box in all of that as our answer. So each time you work on finding the x-intercepts for polynomial functions, you're going to go through this process, set it equal to 0, factor if it's not already factored, and then determine multiplicity and whether it will cross or touch. I think that is, that's the last example before we start graphing. So I'm going to stop here, and I would like for you to go ahead and practice these problems on the homework all the way up until you get to the graphing, and then we'll do the graphing examples in a separate video.